Hello everyone, and thank you for tuning into this presentation. Today, I'm going to walk you through our work titled 3D-ANC, Adaptive Neural Collapse for Robust 3D Point Cloud Recognition. This research was conducted by our team at the AAAI Group, Fudan University, and I'm glad to share it with you in this recording. Point cloud data plays a crucial role in many real-world applications, especially in autonomous driving, robotics, and 3D scene understanding. Deep learning models have pushed point cloud classification to a new level, taking an input point set and predicting one of several object categories. However, despite their strong performance, these models are still very vulnerable to adversarial attacks. Small geometric perturbations, often imperceptible to human eyes, can force the model to output completely wrong labels. This vulnerability poses serious risks in safety-critical applications. So the question we ask is, how can we make 3D point cloud classifiers more robust and reliable? Existing defenses mainly follow two directions. Input preprocessing, which tries to remove adversarial noise, and training-based robustness methods, such as adversarial training or augmentations. While helpful to some extent, these approaches don't fundamentally fix the problem. In our analysis, we observe that the core issue lies in the feature space. In many 3D models, features from different classes are still entangled, clusters overlap significantly. Once an adversarial perturbation is applied, this entanglement makes the model extremely easy to fool. This motivates a different direction. Instead of focusing on the input, can we directly enforce a clean, disentangled feature space? Our idea is inspired by a well-known theoretical phenomenon called neural collapse, which appears during the later stages of training deep classifiers. Neural collapse describes several desirable properties. 1. Features within the same class collapse to one point, their class mean. 2. These class means arrange themselves as a simplex ETF, forming a maximally separated geometric structure. 3. Classifier weights naturally align with these class means. 4. Predictions become simple nearest center decisions. The key takeaway is that neural collapse leads to a highly structured, well-separated feature space, which is exactly what we want for robust classification. So our idea is simple. If neural collapse naturally produces a robust feature structure, can we enforce it explicitly to defend against adversarial attacks? To address this, we propose 3D-ANC, which stands for Adaptive Neural Collapse. The core idea is to replace the traditional learnable classifier with a fixed simplex ETF head. This pushes the model to learn features that align with a clean, symmetric, and robust structure. However, applying neural collapse directly to real-world point cloud datasets introduces two challenges. 1. Class imbalance. Some categories have many samples, while others have very few. 2. Geometric similarity between classes. Certain objects naturally look similar in 3D. To solve these issues, we design an adaptive training framework consisting of two components. The first component is representation-balanced learning, or RBL. Instead of enforcing the ETF structure rigidly from the start, we introduce a learnable orthogonal rotation, allowing the model to gradually adapt the global feature orientation. This approach helps the model handle class imbalance more naturally and stabilizes training, leading to better clean accuracy. The second component is dynamic feature direction loss, or FDL. FDL focuses on local feature refinement. After a warm-up phase, it encourages each feature vector not only to align with the ETF direction but also with the actual class centroid computed from real samples. This provides interclass attraction, making features within a class tighter, and interclass separation, especially for visually similar categories. Together, RBL and FDL allow the model to preserve the strong structure of neural collapse while still adapting to real-world data complexities. We tested 3D-ANC across multiple model architectures and several adversarial attack settings. 3D-ANC consistently improves robustness. The fixed ETF structure and adaptive refinements make it much more difficult for attacks to distort the feature space. TSNE visualizations clearly show that 3D-ANC produces tighter intraclass clusters and clearer boundaries between classes. This confirms the effectiveness of our approach in enforcing a disentangled feature space. Our ablations demonstrate the ETF head alone significantly boosts robustness. RBL recovers clean accuracy and stabilizes training. FDL further enhances both robustness and interclass separation. When combined, the full 3D-ANC framework delivers the best overall performance. To summarize, we take inspiration from the neural collapse phenomenon to build a more robust 3D point cloud classifier. We introduce a fixed simplex ETF classifier to enforce a clean feature geometry. We design an adaptive training framework, consisting of RBL and FDL, to handle dataset imbalance and class similarity. Experiments show significant gains in robustness and feature disentanglement across multiple models. We believe this work offers a new perspective on improving robustness by leveraging theoretical insights from neural collapse. Thank you very much for watching this presentation. If you have any questions, feel free to reach out.